Today, this lesson is called Reflections, and like a lot of math titles, when the lesson starts, you don't know what reflections are. Most math lessons, the title should go at the end of the lesson. You just learned about reflections. So anyways, the title is Reflections. And I'm going to sound like a broken record. Oh, do you even know what a record is? Vinyl disc, and you'd put it on the record player. And here's what would happen sometimes. You'd have there'd be a little break in the record. There'd be something wrong with it, a little scratch. And so the song would go along, playing the record. And then it got to a certain lyric, and it would skip tracks and go back, and you'd hear the same part of the song again and again until you went over and moved the needle over. That's where that broken record comes from, is it literally would be, I don't know any Taylor Swift song. What's a Taylor Swift lyric that I can use? So it would be like, we are never ever getting back together, and then we go again. We are never ever getting back together. And for a while, you think she's just singing it a bunch of times, and then all of a sudden you realize, my record is broken. And there's no way to really fix it, but you went over and you just gave the needle a little nudge, and then the song would continue. So I'm going to sound like a broken record this chapter. Anything I teach, like I'll teach today's lesson, you go, oh, that's pretty easy. I'm like, I know. If I just throw you one ball and you start juggling it, you're like, no problem, this is easy. That's what you're going to do in the homework tonight, going, oh, so easy juggling this one thing. And then as the chapter goes on, I'm going to start going, well, here's 2, here's 3, and you're going to be like, oh boy, here we go. Yeah? So do every night's homework so that you have each thing down pat, so when they all come at you, you're ready to go, which is the way to learn to juggle, by the way. So, reflections. Up to this point, we've investigated transformations on f at x in the form f at x plus k. That was the vertical translations. That was the up and down. I think you thought that was pretty easy. It was pretty nice. Then f at x minus h, which was horizontal translation. That had a little quirk to it, didn't it? Positive didn't go right. Positive went left. And I tried to explain why that was. But it's a little complicated, actually, why it is. A lot of people in grade 11 just are stuck with memorizing it. They go, okay, I'll memorize that. The one inside the brackets does the opposite of what I think it does. So now we'll consider transformations on f at x that have the form negative f at x and f at negative x. You did a tiny bit of this with parabolas, but your parabola experience won't be quite good enough here. It'll help sometimes, but not all the time. So first let's think about what negative f at x and f at negative x really mean. And I really mean, let's talk about it, because when I first write that down, it's probably algebraic nonsense to you. It's like negative f at x, I have no idea what you're trying to say there. F at negative x, I have no idea what's going on there. So here's my first explanation of what's going on here. If I want to do negative f at x, if I want to think about what negative f at x is about, I'm putting a negative in front of this whole function. That is, when I go to write negative f at x, I'm putting negative in front of the whole thing like that. And to step ahead a little bit, I'm putting a negative on the y value. That's the y value, and I put a negative in front of it. We're going to talk about what that means. What happens when you put a negative in front of a y value? Well, algebraically, and see, I'm an algebraic dude, so I like going to the algebra to understand what's happening. Algebraically, life's pretty simple here. I just have to distribute the negative to what's inside. The problem with algebra, and even though I'm an algebraic person, is, yes, so what? So I had the line negative 3x plus 5. Now I've got the line 3x minus 5. Big deal. Well, let's get sidetracked here and get to the bottom of this lesson. Remember on Friday I said there's a moment where, like, if you understand this, you got the whole lesson. That's going to happen right here. I'm going to use Desmos. I'm also trying to convince you to use Desmos whenever you're in trouble and want to do something. So I'm going to go here and go there to Desmos. And here we go, graphing calculator. And what were the 2 lines I was supposed to do? Negative 3x plus 5. Negative 3x plus 5. And let's just stare at that graph for just a second. I'll change the scale a little bit. One of the advantages of Desmos is I'm allowed to change around the scale so I can get exactly a nice picture of this graph. There it is, negative 3x plus 5. Hopefully you're not intimidated by that. You're like, oh yeah, I remember lines. Negative 3x plus 5 starts at y value 5 and goes down by 3s. That's what's going on here. My new graph, and I don't have to look back at the other screen to see what it is. Negative f at x means put negative on everything. Everybody gets a negative because I'm going negative f at x. And again, if that sounds weird, that's right. That's why I'm here today. That's why you paid me to be here today, was try to explain what happens. So if I go y equals now positive 3x minus 5, take a look at that line.
Oh, it flipped.
It just flipped. That's it. That's what a reflection is. If I put a negative out front, this thing flips over the x-axis. Yeah, it flips. That's the mirror, if you want, in this particular reflection. This thing just got flipped over. If you get that, we're home. That's half of today's lesson. Right? You just have to memorize that and remember it. If I put a negative in front of the whole thing, the y values all become negative. You say, the y values didn't all become negative. I'm like, yeah, they did. Look at this 5 became negative 5. It became, the positives became negative. This, where is it over here? Negative 4. If I go negative, negative 4, becomes positive 4. So when we say something becomes negative, we actually mean it changes sign. Yeah, it's a little more complicated than just, oh, it turns into negative. If it was already negative, it becomes positive. Well, that's pretty deep stuff. But maybe pretty simple. Put a negative out in front of the whole thing, see what graph you get. That's different than this. And I'll put this one on there as well. I'll do this one in blue because of my favorite shirt I'm wearing today. I saved it all the way to October before breaking out my favorite blue shirt. This one says f at negative x, and this is a different game. This doesn't say everything got negative. It says only the x is negative. I'm changing the x's from positive to negative or from negative to positive. So when I do that, I get negative 3. Only the x got changed. And if that's weird, well, yeah, it's the first example. You know, it's the first one in there. I'm just saying, I'm telling you what to do. If you do f at negative x, put it in only the x as negative, and what I get is positive 3x plus 5. That's a different line again. I'm going to go to Desmos in a second and show you what it looks like, but I got to get rid of the old one first, or you're going to get confused between the two different versions. I'm going to put the original, negative 3x plus 5, and this new one, 3x plus 5. I'll come back to this if you haven't copied. Let's go to Desmos and put in 3x plus 5. Where was it? I was here. I'm going to turn this one off. Another advantage of Desmos has these on-offs on the graphs. Over here, I can turn on and off graphs. They wanted y equals 3x plus 5. Oh, look at that one. Red was the original. Green's the new. What happened? Still got the plus 5 in it. What happened to the graph here? It reflected on the y-axis. Lesson over. No, not lesson over like, oh, I totally get it. I could write the quiz right now or the test on this. No, what I mean is like, that's what I got to tell you about today. If I put the negative in front of the whole thing, it's reflected in the x-axis, a vertical reflection. If I put the negative only on the x's, only the x's change sign, and I get a horizontal reflection around the y-axis. That's all going to be in the note coming up. I'm just giving it all away right now, saying, what the heck are we talking about here today? Kyle, question.
I don't understand, because it's like, it's 3x plus 5, so shouldn't that mean like it's at the
Starts at 5
starts at 5
and goes up by 3s.
goes up by 3s. Oh, that's the same.
So this one started at 5, but went down by 3s. That's why the horizontal reflection this time, instead of a vertical reflection. I'm going to repeat that like 100 times the rest of the lesson. So if it's just like, oh, I sort of get that, well, we're in great shape. If you sort of get it, we're home free. Okay? Back to here if you're still copying algebra. Now, if you're right on top of things, you might be thinking, didn't we sort of see this with parabolas? I remember parabolas flipping over. Yeah, let's talk about flipping over parabolas. Let's take this back to a grade 10 example. I'll do negative f at x first. And let's see if you're with me. If it's negative f at x, which part of the function gets the negative? All of it.
All of it.
Yeah. There's the algebraic side of this thing. That negative f at x means negative everything. The function gets negative all the way across. So this becomes negative bracket x squared minus 3. The whole thing gets negative. Or some people might start skipping that step. If they understand what's going on, they're just going to be like, oh, just reverse the signs of everything in the question. Well, let's go to Desmos. I'm trying to train you to go, I don't know what's going on. Doing your homework, I can't picture it. So you get Desmos to help you out. What was the original one? X squared minus 3. And again, I'll get back here so you can copy. Just look at what happens on the screen. I'm going to turn all these ones off. Again, the advantage of Desmos, I can leave all those equations in there. The first one is y equals x squared minus 3. Am I remembering that right? X squared minus 3. And let's just pause and talk about that for a second. Just so we sort of remember where we left parabolas. I'm going to try and zoom in at the exact right amount. It doesn't want to zoom in. Oh, there it is. I don't like it. OK, so I can go in here and change my x values. I want to go negative 4 to 4. And y values, I'm going to go negative 4 up to 10. But I want all of the there. See? Don't worry about that for now. You guys are smart. You guys will figure out the settings over there. But if you want to set the graph up any way you want in Desmos, you can. Do you remember this? Y equals x squared minus 3 was the graph of y equals x squared moved down 3. There's the original x squared minus 3. My new function was put negative in front of everything. So it's negative x squared plus 3. Here it is in another color. Y equals negative x squared plus 3. Did it do what the line did? What did the line do?
Reflect.
Reflection. But we're going to need some more words now from now on. Which reflection? Because there's two reflections available. This one's a vertical reflection. It got reflected this way in the x-axis. So the y reflection is in the x-axis. Does that sort of ring a bell from grade 10, though? You had parabolas that went this way, and you had parabolas that go that way. So when you go to, what's your guy? Do you guys have a dance coming up? Homecoming dance? Is that what's coming up? Now you have a dance available. If you don't have any dance moves, you can go now. I've given you some. You've got upward parabola, downward parabola, and you can just be moving around the dance floor like that. The other math people will be like, yeah, I got you. Okay. Let's just jump ahead so we're not surprised about what's going to happen here. If I do a horizontal reflection on this thing, what's going to happen?
Oh, I know, nothing.
Nothing, yeah? And so that's why you didn't do horizontal reflections on this in grade 10, because it's like, why are we wasting our time? But I'll show it to you algebraically, why that happens, why a horizontal reflection is going to do nothing here. In fact, I won't even come back to Desmos. I won't have to. What did I do it in blue? I did blue. F at negative x equals, shh. You're distracting my brain. Sub in negative x to this function. But if I take negative x and square it, I multiply negative x times another negative x, I'm back to positive x. And do you see it's the same function? I don't need to go back to Desmos to see I'm not going to get a new function. A horizontal reflection of this particular function doesn't result in a new function. Any questions so far? Even though all the lesson wants you to do at that point is just algebraically show these. It doesn't ask for too much more than that at this point. So I've really jumped ahead in this lesson to get you to see the whole thing before we get too far into it. And if your brain's exploding on a Monday, look up here, page 1 of 5. We've only got 5 to do today, only 5. Any questions so far, though? Do you need more time? Who needs more time?
Hey, boys, what are we doing over here?
Yeah, if Kyle's quieting you down, you know. No, I'm just going to arm myself here. All I'm going to do is if Nathan keeps talking, I'm just going to on the video say, Nathan, put down your phone about 3 times in a row.
I'm not even on my phone.
I know. That's what's great about it.
That's a lot.
You just said you were gonna lie. Though.
Honesty is the best policy.
Moralizing Catholic values over here, Mr. Todd.
Honesty is the best policy, but it's not the only policy.
Someone's having
Graph paper!
there's no way, man.
It's graphs again. Are you surprised? Well, you shouldn't be surprised. A lot of graphing here. Do you need graph paper still? Who still needs graph paper? He prefers sticky notes. Can you take a couple and pass them around and see if other people need them? Who else needs graph paper? Graph paper? Marley? Dion's giving out sticky notes. I'm giving out for real graph paper. Stupid gravity.
Can I get some graph paper too, Mr. Todd? Greatly appreciated.
Optionally, you may also go to a store and get you some graph paper. Or one of the graph paper notebooks.
I have the assignment.
Oh, yeah.
Want an hour?
Yeah, there's a little pile in the corner of my desk. You can put it there. Anybody else graph paper? You two are like, we are set. Set. Okay, the last examples I overdid. I went and got Desmos to show us what was going on. Now we'll actually do it and walk through it to see what happens here. Using a function that is supposed to be getting familiar. Y equals root x is supposed to be getting familiar. Emma's looking around. No, you've got graph paper, don't you?
Oh, yeah, I know.
What's the matter?
The ruler?
The roller. Ruler. I'm like, first of all, I don't know what roller you're talking about. And second of all, ruler. Rulers are in the big box here if you need one. All right. We're going back to root x because it's supposed to be sort of familiar. But I'm going right back to it to make sure it gets even more familiar. So that root x is like, okay, I know exactly what root x is. If f at x equals root x, complete the following tables. F at x equals root x. Are we good enough at this now to know what x values to use for root x? Yeah. You can go ahead and use -3, -2, -1, 0, 1, 2, 3. Yeah, that's fine. You'll discover that that's a bad choice. But let's do a better choice. Here's the x values that will work good for root x. 0, 1, 4, 9, 16. These are the things we can square root. They're called perfect squares. A couple of you on your assignment call them perfect numbers. I took it. I marked it right. I went, oh, that's pretty good. You're getting there. But they're perfect squares. It means we can square root them. So when I square root them over here, I get 0, 1, 2, 3, and 4. Then I can graph those on my graph. I'm going in red for my original graph. When you're doing these, maybe you want to go just lightly for your original graph. We just need to be able to see this thing so we can compare it with other functions. But I'll go red so you can see it. 0, 0, 1, 1, 4, 2, 9, 3. Notice I'm not looking at my table of values. I've done enough of these that I can do the table of values sort of in my head as I'm graphing. I just go, okay, grab the x values, square root them as I go, and then I'll try and draw this really well. Let's see how I do today. Not bad for me in my active board, actually. Maybe you can't see the points very well. I'll make them a little bigger.
Mr. Todd,
Correct.
it doesn't tell you what x is though.
X is anything. But I'm just choosing convenient x values for points. I could have used 2, 3, 5, 7, 8. So let's say I had chosen 2. I would have got 2, 1.4. I would have got that point there. Just not a convenient point. I would have got the same points. You could go through it and find all the decimal points. You could. But let's just use some convenient ones because the trend is going to be the same anyways. Now, this one says negative f at x. And what we mean by that is I'm going to use the same x values, but I'm going to use, when I use those x values, I got to go negative f at x. So I'm going to write it in here. What I mean by that is find negative root 0. And what's negative square root of 0? Still 0.
Wait, Mr. Todd,
Yeah,
isn't it kind of like a bad example though? Because like,
let's find out. I'm with you, and if you've got a reason why this is a bad example, I'm all for it. Let me finish it off, and then you tell me. Although, if you mean a bad example because I didn't switch colors, I think you're exactly right. I really meant to switch colors. It doesn't affect what you're doing, unless you're trying to color code like me. You don't really need to color code till you make the graph, really. Okay, so back to here. And I want to hear what you had to say, Kyle. I just want to finish the example first before I hear your reasoning, okay? So this was 0, 1, 4, 9, 16. So negative the whole thing. So negative root 0, which is still 0. Root 0 is 0, but negative 0 is still 0. 0 just stays at 0. This one will be different. Negative root 1. What's the square root of 1? But there's a negative out front, so this is negative 1. Then negative root 4. Root 4 is 2, but there's a negative out front. If you're right with me, you're like, I don't need all this writing. When you put a negative out front, you mean make all the y's negative. Hey, that's good stuff. That's good stuff. Negative out front means make the y's negative. But anyways, I'm just going through to prove that. Negative 3, negative root 16, negative 4. And let me put these on the graph. Remember, we're comparing red to blue. 0, 0, 1, negative 1. 4, negative 2, 9, negative 3, 16, negative 4. Are we getting the result that I already gave away and predicted using Desmos a minute ago?
it reflected on the board.
Yes, it reflected. And in a second, I'm going to get to write that in a fancy sentence because you're like, okay, I'm okay with the idea of what you're doing, but I'm scared of the words. Yes, I'm going to get the words down pat in a second. But for now, we just go, huh. All the y values became negative. Just to extrapolate, negative values would become positive. That didn't happen here. Now, back to Kyle. Why was this a bad example?
Because like no, well, I guess it's only for two of them because like a negative times a negative, like the square root and stuff. I don't know, because they will equal the same thing.
Oh yeah, they do come out to the same values, except they've gone to negative, that's all.
Because it's like square rooting.
Yeah, yeah.
I kind of thought, I'm not gonna lie, like the second example, it was just, I kind of thought that was gonna be like the same idea, but you're putting the negative out front. So can you just like solve it without the negative and then just add a negative at the end?
Absolutely.
That seems a lot easier.
Yeah, yeah, I agree. Once you get to know this, this could go a lot faster. The teaching version of this is longer to go, what the heck is going on here? Once you start doing it, you're like, okay, so I just make all the y's negative. Yeah? Okay, well, if that seems pretty easy, just hold on a second. Don't leave just yet. I'll switch to black for the last one. This one says make the x's negative. All the x values become negative. So, okay, so my new function is square root of negative x. Now, when you see those negative x values for a second, you should panic. You'd be like, I can't do square root of negatives. I'm like, it's not going to ask you to. Watch. It says square root of negative x. So I'm doing square root of negative 0. You're like, it's exactly what I just said, Mr. Todd. We're not doing square root of negatives. I'm like, hold on. What's negative 0?
Just
0. So I get square root 0, which is 0. You're like, okay, well, that one was because that one was 0. This negative 1 is going to be a problem. I'm like, okay, let's plug it in. Square root of negative 1. And what's negative 1? 1, and then I'm okay. So don't get carried away with your rule, can't take square root of negatives. Make sure you ask yourself, am I actually taking the square root of a negative? Because this thing asked for the negative, which was positive. Next one, square root negative 4, which is square root 4, which is 2. See, things are going well here. The negative x values are the correct ones to use for this question because we're doing the square root of negative x. Next one, square root negative 9, square root 9 equals 3. Square root negative 16 equals square root 16 equals 4. Mr. Todd, we have to build these tables every time? Like you already told us it was going to be a horizontal reflection. I already knew it was going to happen. Yes, that's why I'm teaching this lesson, so we don't have to do these table values every time. So you can just go, oh, horizontal reflection. It's going to be over here now. I'm using the tables right here, I'm using the values right off the table here. 0, 0, negative 1, 1, negative 4, 2, negative 9, 3, negative 16, 4, and there's the function that way. And I am doing this on the tables so you don't have to later on.
Wait.
Compare the red to the black now. When we went from red to black, what happened? Horizontal reflection with the mirror being the y-axis. And don't get I'll get those words down in a minute. In a second, we'll get all the words down. For now, we're just looking at it and saying visually, what do we see here? Kyle.
Why is the x like negative? Like wait. Like for the third one, the table of values.
Yeah.
Why is it negative? The x is this way.
Oh, well, let's try positive x's for a second. You're right. I did a little bit of trickery there. I went ahead and used negative x values. If I had to use positive x values, what would have happened? Let's go over here.
Same as orange.
If I had gone and used x value negative 4, for instance, and tried to go square root, if I had used x value 4. I said it, but wrote the wrong thing here. If I had tried to use x equals 4 with my new function y equals square root negative x, I would have been stuck with square root negative 4, and the party would have been over.
Oh.
So I helped out a little bit by saying, let's use negative x values. Because if we're going to take the negative of them, that's what's going to make them positive.
Oh, okay.
But you're right, that's not quite as easy as this lesson's acting like it's.
Because if they're positive and x is positive, that wouldn't make sense because.
Yeah. It's because the negative in there, I said, oh, only negative x values are going to work here. Okay. How are the graphs of f at negative x and negative f at x and f at negative x related to the graph? Okay, well, here's the whole deal in red writing here. This is the whole lesson in one sentence with the proper words now. Negative f at x is the graph of f at x vertically reflected in the x-axis. So the idea might not be too difficult. The writing down of the sentence that describes it will take a little bit of getting used to. That was the blue graph. Oh, I should have wrote that in blue. Next one. I will write in black. F at negative x is the graph of f at x horizontally reflected in the y-axis. There. That's everything now. We're just some more examples to try it in different situations coming up. That's everything. It's the visualization of what's going on and the fancy sentences that describe it with mathematical terms, all in one nice slide there. Any questions about that? Oh, it says Y. Ooh, new color, purple. Comma, after you hear comma. Because the Y values changed sign. And here, because the x values changed sign. So the red and the black sentence are like, what's going on? The purple is, why did it happen?
How about we hop off our phones, boys?
Shut up, Kyle. I finished the notes.
Oh, okay.
What did you write?
I wrote down absolutely nothing. I wrote down absolutely nothing. Yeah. Nate doesn't look like
You see what I did there? I turned them all on themselves. Yeah? And now I don't have to fight with them. It took a month and a half, but I succeeded in turning them on themselves. Do you have questions here? More time. Dion, question. Yes?
If we don't really have a question on the test, we can just like draw the first one and then mirror it.
I'll answer yes, but I'm lying. Come test time, it'll be more like vertically reflected and move it up one. Like we're going to have to do multiple things at once is what's going to happen here. So it might not be quite as simple as what you're saying. However, the answer to your question is yes. If I asked for a vertical reflection, you just go, okay, whoop, whoop, draw the original, draw the reflected one. Don't go all the table of values. No, like you can use these shortcuts. Yeah, that's what I'm up to, teaching shortcuts. Yeah. More time here. Here it is, the same thing again. In general, but I'm going to use my red highlighter here for highlighter people. This is like the key to the whole lesson. Right there. In general, the graph of f at x, sorry, of negative f at x. Oh, I don't like the red. Can't read it, can you? How about orange? Tell me how orange goes. Can you read through the orange? Don't overlap, Mr. Todd, don't overlap. The graph of negative f at x is the graph of f at x reflected in the x-axis. The graph of f at negative x is the graph of y equals f at x reflected in the y-axis. New definition. Invariant points. Nice underlining. Do better. Get a straight line underliner out in red. Invariant points. Points that are unaltered by a transformation. Points that stay where they are, and we'll do an example of this, and we'll talk about invariant points, and I hope they don't seem too difficult after you see what's happening. So here's the example. The graph of f at x is given. Sketch negative f at x and state any invariant points. And then sketch f at negative x and state any invariant points. I'll do the first one in red. Need somebody who's right with it. Right with it. I don't say it's hard. I'm just saying. You got to be right with me in this lesson to be able to get this. This first point, negative 3, 2. If I do negative f at x to that function, to that point, where does it end up? What does negative f at x do to functions? It changes the whole equation, which it negative distributes on everything in the equation. So what effect did that have on the graphs? What happened to each individual point?
It changes operation.
Let's go back. I'm going to come back. Those of you who are madly copying, just wait. I'm just going to look at this for a second. Let's talk about this point here, 9, 3. I'll highlight it on this. When I did negative f at x and became the blue graph, where did 9 positive 3 end up? 9 negative 3. The 9 stayed the same. The y value is what switched. Because it was a vertical reflection, the y value is what changed. So we go over here, negative 3, 2, and now we try again. That fast, eh?
Yep.
She can go either place.
Either one?
So it's whatever she wants.
Okay, I'll talk to her.
I'll take care of her here, but
Okay, perfect. Thank you.
no, I don't even have to mark it. It was that easy. Did I give you enough time?
Yes.
What happens to negative 3, 2? Actually, Maggie's got the hand motion here now. Vertical reflections. Yeah, flipped over like this. So negative 3, 2 becomes negative 3. Ooh, not like that, in red. Negative 3, negative 2. Yes, it flips everything. And by everything, we mean the y value, the function value gets switched. If I had 2 in my bank account, now I've got negative 2 in my bank account. What's the next point I got to flip? 0, negative 1. What happens to it when I vertically reflect? Look at, I'm giving it away as I stand here. I can't resist. When I say vertical reflection, it's like an automatic thing that happens to me. When I say vertical reflection, I automatically think like this. Flipping this over. This becomes 0, positive 1. 4, 1. If it gets vertically reflected in the x-axis, becomes 4, negative 1. And 6, negative 3 becomes 6, positive 3. There's what we mean by vertical reflection. So when it was only the square root function, it was like, I didn't say it was easy, but it was very easy to visualize. You got to almost picture this x like a rotisserie type thing where you're turning the x-axis and all those points are flipping over. Now I just need my straight line. Once you see the straight lines, you might really see what this looks like. Can you see the vertical reflection better now? It's not as easy as the square root to see. But the whole thing has been flipped. Positives became negatives, negatives became positives. Same exact question, except f at negative x. What happens?
I just have a question about
This one here, yeah, go.
So how come like the negative 3 doesn't become positive when you times it by negative?
Because I'm not multiplying the points by negative. You ask a good question. If I have the equation, what I'm really multiplying by, I'm really multiplying the whole equation, which is the y value. This is f at x is the y value. I'm putting a negative in front of the y value. And over here, I'm putting the negative just in front of the x value. Yeah? That's just the confusion between equations versus points. That doesn't play out the exact same way. If you want, let me add this to your thing. Flip y values when it's out front like that. Flip the whole thing, where this is just flip x values. Those aren't the fancy words, by the way. The fancy word is horizontal reflection. Yeah? So what this negative 3, 2, what happens to it? If I'm doing f at negative x, only the x's are changing signs, so it becomes over here 3, 2. And here's this invariant point thing coming right at us. What happens to 0, negative 1 when you change the x value? What happens when 0 becomes negative 0? Nothing. So that's what invariant points are all about. That thing there is invariant points are points that after you do a reflection or any other kind of transformation end up not moving. They end up staying where they are. How about 4, 1? If I just make the x value negative, it becomes negative 4, 1. And what's this last one? 6, negative 3. Does it fit in my graph? It doesn't fit. I didn't give myself enough graph. It goes off the end there. It won't be a problem on your graph paper, probably.
0 and negative 1 there.
You can't change that.
Oh, I want it in blue. Weird looking. It's okay right now if you're looking at it going, doesn't, do I see it? You might have to look at individual lines. See this line? 3, 2, yeah, that line just flipped over to there. This line flipped over to there. This one went over there. Yeah, not easy to look at when you first are doing them. You might have to do them point by point and then stare at them and go, how did I do? Does it look like a horizontal reflection? Do you have questions? Who needs more time? Lots of people need more time. All right, that's good. I'll give you a couple minutes there. If you're on the video, you might want to fast forward till the screen changes, because we're taking our time to copy this out. Maybe you need that time. Maybe you're busy copying this lesson down. That'd be good. Ooh.
What's your software? Yeah, there's no glitches in that one. On the 60 it's not.
Still more time? Who needs more time? Yes? Okay. I'm happy. I'm up here doing my cube.
Talk to me when you're on Instagram. It's e-roll. Don't go on those illegal websites. It's e-roll. Go on those illegal websites. That's all you need. That's all you need.
Still more time? Yeah? Pen? Found. More time? We're good? Okay.
10 years. I thought we were done like 20 minutes. No, how it works at all. I thought we were done.
Let's go back to a simple line. Those combination lines mess things up. Let's just go back to a simple one and talk about all the steps again to make sure it's very clear. No excuse me, no Desmos to help us. Let f at x equals 2x plus 1. Write the equation for negative f at x. And this is what Nathan was referring to, is doesn't the whole thing get negative? Yes, in an equation it does. Here's the equation for what I want to do, which is negative f at x. The negative's out front of everything. The whole function gets negatives. So I get negative 2x plus 1. The negative goes in front of the whole function. Is that the way you'll write it? Maybe not. You might be like, I know what's going to happen here. If negative goes in front of everything, then everything gets a negative. Negative 2x minus 1. So now I will do what B says is graph both of them. I'm going to circle that one in blue to graph it. you're supposed to know how to graph f of x equals 2x plus 1. You're supposed to be able to go, oh, the y-intercept is 1, the slope is 2, and you should be able to get points. However, if grade 9 and 10 have just swooshed out of your brain, it's not hard to come up with the points for a line. I don't know that we really did need a shortcut. If I sub in x equals 0 into 2x plus 1, 2 times 0 plus 1 is 1. Yes, I'd prefer that you have it memorized, that you know that the y-intercept is 1. But it's not hard to come up with points. If I sub in x equals 1, 2 times 1 is 2, plus 1 is 3. And then for x equals 2, I get 5. But I hope you're pretty good at graphing lines. Y equals mx plus b. Start at 1 and go up by 2s. That's what a line tells you to do. They were supposed to beat you up with it in grade 9 and then bring it back in grade 10 often enough that you got it down pat. There, label that. Y equals 2x plus 1. That was the original graph. But now, the red graph, they want me to graph negative 2x minus 1. Now what's the y-intercept? For negative 2x minus 1. Y-intercept. Have you just fallen asleep on me, or is it that hard? Negative 1. And now the slope's negative 2, so it's going down by 2s.
Can we stop forcing around?
Nathan, put down your phone, please.
I'm not even on it. No way.
You're,
I'll see
you're coming to parent teacher interviews.
I'll see you there.
Oh, that's good. I'll just play this video. I just want to show you one thing, I'll say. Okay.
Friday's video was
What happened between the blue and the red?
Friday's video would be a good example because I was in it. I was the dancer.
Oh, yeah. You were sort of in it. You could hear we were doing something, but you don't get to see it because it's not an actual video of the lesson, is it? Can you see the vertical reflection? All the blue points became the negative of themselves. Yes? 1 became negative 1. 3 became negative 3. 5 became negative 5. Okay. It says determine any invariant points. This is easy if you have the graph. What's the only point that's on both the blue and the red? It looks like about negative 1/2 comma 0. That's what it looks like it is. I mean, it is negative 1/2 comma 0. And the domain and range is not exciting here. Lines are domain, I'm having trouble with the pen here. Domain, 3 times in a row.
Nathan, get off your phone. Even Andrew said it. You need to let me do it.
Both of these have full domains and ranges. So it's not a very exciting question, really. But we bring up domain and range every once in a while just to make sure we remember how to write these things. Oh, and my purple point lost its bracket. Okay, I don't know if this is a tough question or not. Let me just ask this. For a vertical reflection, which points are going to stay invariant? 0, yes. What specifically type of 0?
Like positive 0. X.
Yeah, the ones that have on the x-axis that have their y value 0. So it's the x-intercepts that stay invariant here. So for horizontal reflections, you'll see that the y-intercepts are the ones that stay invariant. Okay, that's slide 4 of 5. Who needs more time? I'll take my time and mess up my problem for today. Is anyone watching this and it's really bothering them that I'm messing this up? Some people actually, that really upsets them. They're like, don't do that. Folks, if you did a quiz or an assignment on Friday, I marked it, but didn't update the marks yet. And I thought I would get time at the end of this lesson, but the lesson took a little longer than I thought. So I will do it. Just come to the math help room at lunch, and I'll have your updated mark. If you handed me a quiz or assignment on Friday, those of you who handed it to me today, I will try to get to it tonight. Yes? So I'm trying to get updated and stay updated for parent-teacher interviews so that if your mark wasn't where you wanted it to be, maybe it's a little bit better for parent-teacher interviews. If your parents had trouble with the online booking system, just have them email me, and I'll figure out how to fit them in, okay? Did that buy you enough time? Yeah. Is it good? Okay, last slide. Example. F at x equals x plus 5 squared. Write the equation for negative f at x and f at negative x. All right. Before I release you to do homework, when I put the negative in front of the function, where does the negative go? In front of the whole function. So that's this thing. And before I multiply it in, I like the way it is now. And it's my job over the next couple of days to go, I like this fine. I'm not going to multiply anything out. I'm not going to do anything. I like it just the way it is. I'm not going to do anything else with the negative. Whereas this one, only the x becomes negative. Now, I don't like that, and we've got to work on that, but we'll need one more lesson before I deal with it. So I'm just going to leave those the way they are. That's all I want you to see so far, is negative f at x, you put the negative out front. F at negative x, you just put the negative there. And I'm going to try and do what Dion suggested, is don't do a whole table of values here. Let's just try to graph these functions straight up. Here's what I'm going to use. In orange, I'm first going to use y equals x squared. That one, I hope you're familiar with. I could build a table of values for y equals x squared, but I'm not going to. Now I need a juggler. I need a juggler to tell me if that's y equals x squared, where's y equals x plus 5 inside the function squared? Yeah, I've been talking about reflections all day, and now I'm reaching back to Friday's lesson and going, what happened if it's plus 5 inside? Where does it move to? Left 5. Do you see? Maybe you're just starting to get an idea of why this is going to get difficult, is because we're going to have to balance all these different things. So I'll move those all left 5. Here they are. Oops. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Shh. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's Friday's lesson. Take y equals x squared which I will label here. And move it left 5, which I will also label here. Y equals x plus 5 squared. Now, without without any table values, without doing any other trick, what's the blue graph going to look like? It's negative x plus 5 squared. A negative out front of the whole thing. What do I get when I take x plus 5? My hands almost gave it away. I need to know what that negative out front does. What does it do? Moves it down.
And it moves it.
I've already done this far, the left 5. That I took care of. If I just put a negative out front now, what effect does a negative out front of a function do? Vertical vertical reflection. Yeah, do you see now the problem? It was all fine when all we were talking about was reflections. But in the middle of doing a left-right transformation, this negative out front is like, what does it do again? And it's this. It does a vertical reflection. And so I don't need a table of values. I just take the black graph and I reflect it vertically down like that. Does that answer your question, Dion, about whether it's just that easy or not? Because I said sort of it's that easy. Left 5, but then reflected down. Yeah? Now the horizontal reflection. If the negative is inside, the black gets horizontally reflected. All the x values get turned negative. Well, they were negative, now they're positive, so now the function's over here. If that has your full attention, like, oh, this lesson was really easy right up into that last slide, yeah, you're starting to see the juggling thing that I was worried about. Sorry, it's got a little hitch in it because that's my active board. It doesn't draw straight. See, it's got a band of magnets that are out there, and it doesn't draw straight lines very well in those sections. Determine any invariant points. There was an invariant point of negative 5, 0 in the first transformation, but there wasn't any invariant points in the second transformation that we could see. Which point would be invariant that goes off the screen here? I don't know where it is, but it would have been the y-intercept when it got there. And finally, domain and range. Domain and range for the blue one was x element of reals. And for the red function, I don't have any specific rules about domain and range here. You have to look at the graphs each time to get your domain and range.